Good day, everyone, and welcome. I'm Jack Van Horn from the University of Virginia, and I'm proud to welcome you to this edition of our 2021-2022 Foundations of Biomedical Data Science Seminar Series. This lecture series is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA Brain Institute, the College of Arts and Sciences, and the School of Data Science, and through a grant from the National Institutes of General Medical Sciences. This year's theme is Ethical Challenges of Artificial Intelligence in Biomedicine, where we will enjoy presentations on Fridays from leading thinkers about the promise, opportunities, and hurdles which are associated with AI applications in the biomedical sciences. Selected participants in our Biomedical Data Science Innovation Lab program will leverage these presentations as vital material for our culminating in-person grant project development workshop to be held here in historic Charlottesville, Virginia in June of this year. Applications for the Biomedical Data Science Innovation Lab program are still being accepted until January 31st of this month. And so if you are interested in this topic, please consider applying, and we encourage your junior colleagues to do also. We look forward to reviewing these application materials. It is my honor and privilege today to welcome our speaker, Dr. Claudia Perlich, who works for 2 Sigma. Claudia has worked as an adjunct professor teaching data mining in the Masters of Business Administration program at the New York University Stern School of Business, where she received her PhD in information systems in 2004. She previously has worked at Distillery, where she served as chief data scientist from 2010 to 2017, and also as a research staff member in the data analytics research group at the IBM Watson Research Center from 2004 to 2010. There, she led teams which competed successfully in KDD data mining competitions, designed and executed wallet and opportunity estimation models for IBM sales using quantile regression, and worked on blog and Twitter data analytics, all sorts of things. In continuing our 2021-2022 Biomedical Data Science Seminar Series theme, Claudia's lecture today is entitled The Secret Lives of Predictive Models. In the context of AI in general and learning predictive models in particular, predictability is usually considered a very good thing to have. That is often the goal: build the model that has the highest predictive performance. Indeed, the rise of big data has in fact been vastly improved by our ability to predict human behavior, thanks to the introduction of more informative features. However, as Claudia is going to describe for us in practice, things are a little not quite what they seem. And she is going to share some practical lessons about when models had a surprising secret life and did something very different from what they were expected to do. She will remind us that as creators of machine learning solutions, it is our responsibility to pay attention to the often subtle symptoms of these challenges, and to let our human intuition be the gatekeeper deciding when our models are ready to be released into the wild. As always, we are streaming this lecture live and for recording via YouTube. If you are watching on YouTube, thank you so much for joining us. Also, our specially selected 2021-2022 Biomedical Data Science Innovation Lab participants are strongly encouraged to submit any questions for Claudia via the chat feature in their Zoom sessions, and I will synthesize these questions and ask them on their behalf during the last 10 minutes or so of the lecture. And with that, welcome, Claudia. We thank you so much for doing this for us, and we cannot wait to hear what you have to tell us.
Thank you so much for the introduction, Jack, and it's a great privilege to be invited to speak here. So you know a lot about me already, so I wanted to jump in. Having been working on predictive modeling pretty much all of my life, I had some reflections one day when I, for the first time, watched a show called Person of Interest. Not sure if you come across it. Basically, the premise: there is an all-knowing AI somewhere underneath here that can predict with absolute certainty which person will die a violent death in the next 24 hours. And aside from enjoying kind of the dynamics of it, on the other hand, it gets me really upset when I see this in the media, because it creates this expectation that models can be perfect. And so as a result of this, I've been pondering for a while now, well, how good can models actually be? And what do we need to understand about how good models can be? So I want to frame this as the question of how predictable is a predictive modeling task. And I want to make it clear that this is a function of the problem you're trying to solve, in addition to the data and the algorithm you're using. And so in my mental mind, I have the spectrum that there is stuff that's really hard to do. That's kind of where my day job is today. So we know that there are tasks where you can barely perform better than random. And that's, for instance, true in predicting stock market returns. Efficient market hypothesis basically says you shouldn't be able to do that, or at least not very well. And then on the other end of the spectrum, you see a lot of problems where we have made great strides with the rise of deep learning. Things like, is this a cat? This is inherently a much more deterministic problem. I'm not saying it's easy to do, but any 3-year-old is a lot better at telling whether this is a cat than your wealthiest financial advisor at picking stocks. So in this kind of framework, my last 20 years, I've pretty much operated in this weird middle ground of human stuff. And some of it could be medical, but a lot of it is also about our behavior. And what I found interesting, that even with regard to how we behave and how predictable, there's a lot of nuance. So on one hand side, there have been studies based on Facebook data showing that there's a lot about us that is predictable if you just see a lot of the things that we do. And examples here are religious affiliations or sexual orientation. On the other hand, I have no idea what I will have for dinner. Depends how hungry my son is when he comes from school and how urgent it is that I go and grab a pizza. So things about my day-to-day fall also into this spectrum. And I like this mental framework because it will be important in understanding some of the secret lives that models have, depending on where they're operating in this spectrum. So let's actually get into this and dive a little bit deeper into a simple problem here, where right now, all I'm trying to predict is gender. So I have a large set of people, and I actually got data from a public Facebook data set, where I'm going to try to just build a AI, machine learning, whatever you want to call it, to predict whether or not this anonymized person is likely male in this data set. So we have about 200,000 people, and you see the anonymization on top, and there's a column that indicates the gender. In addition to this, I have a lot of their activity, and it's again super anonymized. So what you see on the right is basically a sequence for each of these IDs. We see things that they liked. So the column on the right is basically hashed IDs of articles, pictures, comments that they have liked in the past. So with this as the code set up for a little experiment, I'm going to use my favorite model here. That's a logistic regression, but I don't think it matters, to try to build models to predict gender. Okay, so take one. What do you think is going to happen if the only feature I'm going to use is the age of the person? How well do you think you can predict gender if the only thing you know about a person is their age? So let's take a look at a model that is really pretty clueless. The overall accuracy is 60%, which shouldn't surprise you if you observe that the base rate here of males is 40%. So if you only predict female, then you have a 60% accuracy. The second measure that I'm reporting here is what's called the AUC, which is quite commonly used in evaluating ranking models. So it tells you the probability that the model will assign a higher predicted probability to a true male person over a female. And the AUC typically has a range between 50% to 100, where 100 is perfect and 50 is clueless. So we're a little bit better than clueless, but yeah, not by much. The important part is not so much the summary statistic, but it's to understand what the distribution of the predicted probabilities actually looks like. And here is now on a holdout, the distribution of the predictions. And you would see that they are nicely centered around 0.4. If I'm trying to be statistical, I'd say looks vaguely normal, with a mean slightly above 0.4, and we see a little bit of a spread. Now, many applications that I've worked on, you don't really care about all predictions, especially when you work in advertising or even in financial industry of picking stocks you truly believe in. What you really care about are those predictions that are at the outside, like at the tail end, highest or the lowest. Let's take a look at what the highest predictions are here. So in the top 1%, if I rank it by probability of being male, it actually turns out my model is not as bad as I thought. I'm getting an accuracy here of 75%. That's decent, not overwhelming, but all right. Now, let's try this again. And this time, I'm going to add a lot more features. So not more examples, but I'm adding additional information to the exact same column, exact same examples I already had. So now I'm adding all of the information about what people actually liked. And should be no surprise that the expectation here is that you can do a lot better, right? So you should see much better performance. Accuracy is up to 83%. Not great, honestly, I had hoped for more. But what's really important is this very different picture of the distribution of the predictions. This is a model that is very opinionated. It knows that it knows something. So you see these two sides where you have a lot of probabilities very close to 1, very close to 0. And then you still have a little bit, if you look at only the highest predictions, no surprise here, they're all male. So we got this one perfect. If we really only care about the top 1%. Now, if I have a live audience, I then tend to ask, there's something here that should catch your attention. So what is going on with those folks right there in the middle, where the model is still highly unconvinced what the correct gender is? And the answer is, these are all the people just didn't like anything. So basically, it's a subpopulation where a lot less information is available. And that will come back and be relevant in a moment. So why did I show you this? I think it's important to understand and to develop an intuition for this progression that you see in the distribution of model predictions as the predictability of a problem increases. So initially, looked kind of normal, 75% correct in the upper 1 percentile. If you start adding the 10 most commonly liked things, so it's not the most predictive, but just the most common things that people like, your performance in the top 1% goes up, and you start to see that distribution widening a little bit. And this trend continues. Now I'm adding 100 features, 1,000, 10,000, and finally all 100,000 things that people could have liked. And now you see this clear spikiness on the left and the right for a problem where you have a very high level of predictability. Now, while this is nice in this little example in Facebook, why is that relevant in practice and to maybe what you do? My experience is most problems, most data sets have a mixture of things. Some parts of it behave more like the financial industry with very low predictability. And then other parts of it have a lot more of that almost deterministic behavior. Now, what's going to happen to your model if you have these kind of mixtures? And I'm going to now pivot to my day job through 2010 to 17 when I worked in advertising. We built large-scale automated systems that built hundreds, if not thousands, of predictive models every day that would basically try to forecast which customer might be interested in which product, might be interested in clicking on something. So we had this whole collection of models that all predicted something else. Some were for luxury cars, other were for pizza. And what we observed tracking these, that there was a period in 2012 when the median lift across many of these totally different models increased by about a factor of 2. Now, I have a hard time understanding why people all of a sudden should become more predictable. We have a certain level of free will, I hope. And so what could cause this increase in predictability across many different problems? So we spent some time looking at this, because while it's great to report to your boss that, hey, you increased the predictability or the performance of your models, I knew I hadn't really done anything. And what we found were these odd websites like Women's Health Space that seemed to have some semi-relevant information about health for women, but that also indicated that whoever came to this website then had a very high probability to sign up to book a hotel room, order pizza, sign up for a new credit card, showed interest in Microsoft Office software and luxury cars. We spent more time on this and found a bunch more URLs that seemed to be very predictive for many different things. And if you look at this, I would be surprised if any of you has ever seen one of those websites. So what's going on here? And as a first attempt at understanding this, we started to look at the overlap between the populations of people who go to these websites. So to give you a sense of the analysis, we are trying to create this graph where we are looking at the overlap between populations that show up on 2 different websites, and we will create links whenever that exceeds 50%. If you want to know why I have this data, ping me on LinkedIn, and I'll share more about the dark sides of the advertising world. So to give example, and it has a 55% overlap of its users with YouTube, 28 with weather.com, and you see kind of ranked by the number of percentage of common users, it going down. So if I had an audience, I would ask you to guess what it is. I'll give you a second to think about it. It's not Google and it's also not Facebook. It turns out that it's the New York Times. And if you look back at it, it kind of makes sense. There's a lot of New York stuff and also new stuff going on. So that's kind of understandable. Let's look at a different example. So here's a website where 96% of its visitors also go to Film Annex, 93% to Fork.net, and you see a whole bunch more of these weirdly predictive websites showing up. So anyone wants to guess what that is? Well, it's Hip Hop Havoc, of course. What's going on here? Something really odd. If you put this into the larger context of the entire internet, you're starting to see an interesting collection of structures. So this is a visualization that we did, only including websites with enough traffic that are connected. And to give you a sense, let's look at one of these smaller structures here. And this is the Boston Herald with a lot of related websites or technically integrated websites. So I think that makes sense that this is human behavior of people who are interested in Boston. But let's go back to our center here, this weird clump right there in the middle. And so this is actually where our friend Women's Health Base live. And there's a whole bunch of weird other stuff around it. So you see this dense connectivity of things that really have nothing to do with each other. So as far as I'm concerned, there's no way that this is human behavior. So what you're seeing here, maybe not surprising, is basically the digital footprint of a bot network that was created of defrauding the online advertising industry. So all of these websites don't really get real people visiting them, but they are showing a lot of ads and they're being paid a lot of money for showing ads to bots. Okay, if all I told you so far that there are bots on the internet. Who cares? I mean, that's not surprising. But what has this to do at all with my problem, or not problem, that my models get a lot better all of a sudden? So what happened in this time period is that the type of fraud had changed, and that the fraudster had discovered a really cool mechanism of making a lot more money. And that was called cookie stuffing. So if you own a bogus website like Women's Health Base, and you hire some dude to write your bot to visit your bogus website so you can basically sell ads to that bot, you will get a lot more money if prior to coming to your website, that bot goes and visits a whole bunch of famous brands that spend a lot of money on digital advertising. Because now these are all what's called retargeting opportunities. Advertising a lot of money, typically follow you around with that one pair of shoes that you looked up 3 weeks ago that you continuously see popping up in your browser no matter where you go. That's called retargeting, and there's a lot of money in it. Now, while it's annoying for the user, it creates a huge problem for me, because these bots now take exactly the actions that I'm trying to predict. So my target variable now is also populated by the activity of bots. Who is who? We did an analysis where we looked for different of these advertising relevant conversion events. And so the winner here is, so to speak, the Clorox video campaign, where we see about close to 70% of all of the video completion is actually done by bots. I mean, only bots are patient enough to sit through all of these Clorox videos. But you see the scale of the problem, that you have this activity, quote, poisoning my target variable. Now, what I'm essentially pointing out here is that you have exactly this scenario of mixed population. I'm trying to build a model where some proportion are people doing people things, and then some proportion are bots doing bot things. And so that ratio grew from initially 5%. I think in 15, we observed 36%. There's a lot better bot detection today, but I think it still hovers roughly in that area. But what's important here is that when it comes to the question of how predictable this is, people are random. Where bots are programmed to do this. They are programmed to go and sit through the Clorox video. And as a result, if I have this mixed population in my training examples, I get this weird scenario where all of the predicted probabilities for people are somewhere in the middle, where the model isn't quite sure. And then all of the extremes, the very large or high probabilities, are purely bots. So even if the distribution initially was, my target point will only try to show ads to bots, which is arguably not particularly productive. So that's an example where we spend a lot of time trying to understand what the hell our model was doing. And eventually we implemented a bot detection algorithm that removed them from the training data, and my performance went to hell. But for once, that was actually a good thing. Quick comment, if you care, what about clicks? Exact same problem. Clicks have similarly this property where part of it is human behavior, intentional interest in products, and other ones happen at random, except that they don't happen at random, they're accidents. So it could be because you're not paying attention, it could be because the lighting is bad. So we see a lot of very strong click activity, irrespective of the product, in specific apps, many of which are flashlights, where people are stumbling around in the dark and accidentally click on ads. And again, you have the issue here, clicks predictable than the intentional ones. And so most of the targeting ends up hunting for accidental clicks, whereas the people who might in fact be interested in your product will not be reached by the targeting, because the model kind of navigates inherently towards wherever the signal might be. Let's look at an interesting counterexample and its implications. So basically, I told any online conversion events. So from an advertising perspective, where does it leave you? Well, things that are hard to fake or do by accident is going to a car dealership. So what we try to do, we try to identify people who have a high probability to show up at a Mercedes-Benz car dealership. Now I have to come a little bit cleaner around the data that we actually have. So at Distillery, we basically collected online activity across devices. So you have your web activity on your laptop, but you also see activity on your mobile devices on the right side. If you have your GPS switched on, I also get information about your location and where you're currently hanging out. All of that gets connected through your home IP address. So I can now use your web activity and try to predict or build a classification model to identify who would show up at a car dealership. Now, there are a couple of issues with that. First off, it's the location data available in AdTech is not particularly clean, and we will comment on data quality in medical areas in a moment. A second area problem is that I may not get the connection to your laptop right. So for instance, if you sit at a Starbucks, then your browsing history is totally different, or maybe your neighbor hacked into your Wi-Fi, and while you have been to the car dealership, I'm actually observing the browsing activity of your neighbor. But let's assume that works out somewhat. What I'm going to do now is I'm using the URLs that people visited as features in a model to predict whether or not they go to a car dealership. Now, I touched on this, and I'll give you a bit of a flavor of issues with location information, where what we're observing in terms of the location that people are in is highly problematic. So you see artifacts, for instance, about 30% of users of smartphones seem to be travel faster than the speed of sound every day. Clearly, there's something not quite right. The other thing that you're observing is so-called people stacks. So you see locations within the US, it's actually a cornfield in Kansas, where at any moment in time, there are about 100,000 people sitting right on top at the exact same GPS. And the reason is that's the geographic center point of the US, and a lot of GPS systems, if they don't want to tell me where you are, then they only tell me that you're on the US, and then somebody replaces that information with the center point of the US as the lat long. Another thing that you see is this pattern here. If you squint at this graph on the right, you see this odd striping. There's a little bit of other stuff going on, but you see these horizontal lines and these vaguely slanted vertical ones. And that's basically rounding error. So when you round the lat long, that's when you get these artifacts. People aren't exactly at this place, but the machine interprets it as location 00 in the rounding, and therefore it seem to be. So I gave you a lot of good reason to not trust my target variable, because I don't know for sure whether or not you actually were at that car dealership, or maybe just in the coffee shop across the street. So what that means for our prediction task, we have really three different populations in here. So we have people who are indeed at the car dealership, so where the one in my target is correct, and their correctly associated history. Then I have people who were the car dealership. So that's a kind of a false label as positive. And then you have people who may or may not have been at the car dealership, but I have the wrong features associated with them because, say, your neighbor hacked into your Wi-Fi. What's going to happen if I'm now going to train a model on this scenario? So here's the model, and what you see on the right are the parameters of a logistic regression, where it's ranked. So you see on top those URLs where people who have this predicted probability up at that Mercedes-Benz car dealership. And it's actually surprisingly good. Let's look maybe into a little bit more detail. So there's a lot of car stuff going on. I mean, there's Mercedes, there is a bunch of other car related, you see other brands of cars that people might be considering. So that's actually quite surprising. You also see real estate. So there is this old myth that I thought was a myth in advertising, that people who also buy real estate. And those of you who recently during COVID moved out into a slightly more rural area would certainly testify that, yep, if you buy a house outside of the city, you need a car. So we see evidence of the model picking up on this. Also see some upscale fitness. Well, it's Mercedes-Benz, so you can imagine what type of person buys a expensive car and signs up for a very expensive fitness center. In any case, this is interesting in the sense that of those three populations, the ones who actually went to the car dealership and I had the correct history are where the signal is. And all the other stuff, the people where I had the wrong location information or the wrong history, receive very low predictions because they are near random. The model can't find any signal. So in fact, my model almost acts like a low pass filter where my predictions may in fact be more correct than the labels I had on my training data. Because it only focuses on what, quote, has information and makes sense. So in this case, it actually worked very much in my favor that the model so much focuses on where the signal is. There's a little experiment that I did where I was really curious to see, well, how bad can my random labeling be before my model falls apart? So I'm going to take this data set again that you can download if you want to reproduce it. And so I'm a task here of predicting who's male. Well, it's still predicting who's male, but I will start to randomly reassign labels. So for these rows, I may randomly pick the opposite or the same and train my model. And on the test set, I retain the original labels. And I want to see how bad can my disturbance get before the model falls apart. And what to me was fascinating is you could mess with almost 50% of the labels before you see a significant decrease in the accuracy in the top 1% prediction. I'm not talking about overall accuracy, but if I'm only looking at the highest prediction, I still get a vast majority of correctly identified males. And here you see how that model kind of gets clearly more uncertain about what the hell might be going on. So it's kind of wider, but you still see these spikes at the end for the subpopulation where the data made sense and it was more predictable. So since this worked so well, my final example for advertising, I promise, we'll move to medical applications in a moment. One of the things advertisers love, the group of people are frequent travelers. They probably have a job that pays enough, so they have enough income to buy a whole bunch of things. They might also be bored sitting around waiting for their flight and therefore have time to look at ads. And they may even have a bad conscience being away from the family for so long, so they might want to buy gifts. So great audience to target. What do we want? How do we find frequent travelers? And since it worked so well the last time, let's this time predict who will show up at JFK. So we're now going to build a model similar to the one for the car dealership, but this time we're predicting who will go to JFK. And here's the model. Same as before, I rank the most predictive URLs that indicate that somebody will show up at JFK. I'll give you a second to peruse this interesting list. All right, so let's do a bit of a deep dive. Let's start with some religious content, often in Spanish. The plot thickens. There is Jump Seat News, flight attendant resources. And then finally, a bunch of sports stuff. So I don't think that what we found here was the elusive frequent traveler with money, but what the model basically figured out who has to be at the airport, the people who work there, the flight attendants, the baggage handlers, all of those. So the people I'm targeting here are really just people who work at the airport. There's a really deep implication of that regard to biases that I will get back to towards the end as I'm opening this up more for discussion. But I did promise to touch on stuff related to medical applications. So I have tinkered with medical applications a couple of times. I volunteered to help with a readmission prediction for a rehabilitation hospital called Berkey here in Westchester. And so they were interested to see if there is evidence that you can find with AI, whether rehabilitation indeed improves the outcome for the client, the patient, as well as the hospital by reducing the probability of readmission. So we got very detailed patient data, including medical records, diagnosis, medications, as well as information about the most recent hospital stay. And we set it up as a model to predict the probability of readmission. And the model had a lot more information, but I will show you just the component that was relevant to Berkey, where we're only looking at the parameters on this logistic model for different post-hospital care models. So these codes here, PS06 through PS65, they're basically capturing what happened to the patient: sent home, sent in a nursing home, went to rehab. And the parameter estimate is the impact of this action on the probability of being readmitted. In particular, this is the rehabilitation treatment. So PS62 means the patient was transferred to rehab, and good news in some ways, we actually see that it seems to have a decreasing impact on the probability of readmission. And this model actually controls for a whole bunch of risk factors that I just didn't include here. But there should be one thing you really want to know more about. There should be one particular case that you want to understand better. At the very bottom, PS65 seems to have a huge increase probability in readmission. So who are the people, or what happened to them, that seem to suggest that they have an extremely high readmission rate? And it turns out what this code is meant to capture is that the patient, now that should be very predictive of readmission, but not the way it looks. In particular, what we're seeing right now is if the patient passes away, then the probability of readmission should be 0. But what we see is an increase in the probability. And it turns out what happened in this case was something that had been basically part of the pre-processing. When the data was created for me, based on whoever had access to the transaction level data set, they basically just, for the target variable, they defined readmission of having a subsequent event at a hospital in less than 30 days. So readmission is anybody who has anything within 30 days of leaving the hospital. So they basically just put a filter saying if the time to the next admission is less than 30 days, that's a readmission. But people who passed away, this time to the next event should be infinity, except that whoever was running the database didn't know how to put in infinity and instead coded people who never came back to hospital with 0 days to the next event. So meaning everybody who passed away automatically was labeled as readmission, and everybody who was actually super healthy and never came back was also coded as a readmission. So this is a huge problem and basically means the data is entirely unusable for what we're setting out to do. There is the fundamental problem that you should include in the model whether or not somebody passed away explicitly, even if it happened after being sent home, because obviously those people wouldn't be readmitted, and that's a different case. But we still can't really tell apart whether not coming back without knowing that somebody passed away, whether it's either a good or a bad sign of health. So you get these very muddled information in the severity of the case if both very healthy and dead people end up having the same label. So the point I'm making here is data errors are a hell of a lot easier to predict than readmission. And if you think that this is a rare case, there is a lot going wrong with especially clinical data and patient records, and having very close control and understanding of your data collection is incredibly important. Another example in a similar vein that is a lot more subtle, but arguably with as big implications, is a task where we were trying to predict or identify breast cancer based on fMRI images. So we were given subregions in images that were featurized. So you had 117 numeric features representing a region in an fMRI image. And it was labeled, and we were trying to identify the probability that this candidate region was indeed malignant. We worked on this. That was actually in the context of a competition, and the data had been originated and donated by Siemens. And so we came up with a really great model. So it did incredibly well. We had a very nice increase in performance in terms of this true positive rate relative to the false positive rate per image. And so the equivalent of an AUC here is something like 93%. And we also were very good at identifying people who were with high probability healthy, meaning had not a single candidate region with a probability or a large probability of cancer. So about 60% of the cases, we were very confident we could identify as healthy. So looked great, all good, except at some point, and that was more accidental than anything else, we observed some weird behavior when we started looking at the model predictions vis-a-vis the patient ID. Now, the patient ID technically should be a random number assigned by the hospital to the patient, and it's not the thing you would add to a predictive model to identify whether or not somebody has breast cancer. It turned out, if you just look at the graph here, on the x-axis is the log of the patient ID, and you see these very clear groups, right? So there are a bunch of people below 20,000. There are some in the middle between 100 and 500,000, and then there are a lot of patients with above 4 million, which, you know, it's okay. The problem is the patient ID is exceedingly predictive. So you see in the lower group, your incident rate is high with about 36%. In the middle group, you only have about 1%. And then in the outer, on the large side, you have some people with 85%. Without even looking at the image, I can tell you the probability of cancer is 85%. And some where I can also say with certainty, probability of cancer is 0. What's the story and what does that mean? There's a good question whether or not you really shouldn't use the patient ID for your model, because what it really does, it proxies for the location of the fMRI machine. Clearly, the provider of the data, Siemens, had given us data that originated from multiple different locations. And presumably, because these are rare machines, some of them were treatment centers and others were just screening centers. Now, from a medical perspective, it's important to know whether or not that image originated in a treatment center, because your prior on it being malignant is very high. So in some ways, this is what the model should do. But what it really means that the model has accidentally picked up basically the average grayscale, because even without giving the model the patient ID, it would still learn primarily the location effect. And what you end up with the model is really, it predicted where the location was, and the calibration of the machine that was used to collect your data then actually learn how to detect cancer. So what's the big picture here? There are a couple of lessons that I hope you can carry over in your future applications of machine learning in medical application. I think the one that to me was most eye-opening is that models can in fact create biases, and the underlying driver of this is this inherent predictability of different subpopulations. And this is in addition to biases that you may have in your data set explicitly. So here, for instance, in the training, the travelers outnumber employees by about 15-1. But when you look at only the highest predictions, the employees outnumber the travelers by a factor of 10-1. So you cannot rely on the fact that your predictions will mirror the basic distribution of your training data overall. And so to really demonstrate this, I went back to that data set from Facebook, where now I'm not predicting gender, but I'm predicting something else. And in particular, I pick certain likes that have even interest by men and women. So I pick a thing that men and women liked, and now I build a model based on the other features to see who would be liking this one thing that I picked as my target variable. So we pick something, and now we build a logistic regression that predicts that. And what I'm interested to see is what happens to the gender distribution. And here's an example of what we're seeing, where if you look at a decreasing sort, so with the highest probability of liking this thing, in the top 1% of predictions, there were exactly 0 females. Whatever this thing is, the most predictable group are males. And in that part of your prediction, you only had males. And then over time, you see, as you kind of went down with your cutoff and looked at larger ranges of predictions, you ended up having more male to female ratio. But this has huge implications on things like job recommendations, where you're worried about not getting enough female applicants. Even if you balance the data set beforehand, you may still end up with all of your highest recommendations being one gender or the other. It's not always detrimental to females. It's just whatever is more predictable, that's what the model will end up recommending you. So what are some of the takeaways leading into the questions? I think my general rule is you have to know your data. There's no way around it. And I actually dislike it when my data sets are prepared by somebody else. I find in the medical domain, it's often hard to really understand how the data was collected and pre-processed, but it's incredibly important to see that. The second piece of advice I have, it is always very interesting to really deeply understand what these most extreme predictions are, either the highest or the lowest probability, and deliberately hunt for distortions there. My third point is, a lot of people talk about debiasing alongside with model transparency. But if you think about my breast cancer model, there is nothing in the model that would tell you that there is this problem of it really having only learned the grayscale. Being able to identify this as the root cause, it really comes from the underlying data. And so I think transparency is good, and you saw this in the advertising models, but it is not sufficient. The same way that debiasing your data set isn't sufficient, because your model can create biases by itself. And that means that we have to take ownership at the prediction and action level to test for biases and to correct them at them. We cannot rely on the various mechanisms that have been proposed to would force models to be unbiased, I don't think they fully rise to the occasion. And so my general attitude is, rather than forcing models to be debiased, I'm more interested if, for instance, you want to invite an equal number of male and female into your interview process, to basically do so and just have the model give you the top female and top male, rather than trying to somehow get it to be perfectly unbiased, which I don't believe is necessarily possible. So thank you very much. I think we have questions collected if there are any. I want to close by, I would love for folks to reach out to me on LinkedIn, write a sentence or two about having seen me here, so I don't dismiss you with other folks. But yeah, I would love to get to know some of you, given that we have to do all of this via Zoom here. Thank you.
Claudia, thank you so much. I'd like to remind any of our participants who are joining us here on Zoom to send in any questions they have for Claudia in the Zoom chat. And while we're waiting for that to happen, Claudia, that was fascinating. And you touched on so many things I think have affected almost every one of us in some way or another, certainly with our online browsing behaviors. This is just a personal thing. It just happened with me and my family. Is we just had this big snowstorm. Many of us were affected here on the East Coast by this. And we lost our power at my home for a number of days. And my wife was kind of actively trying to figure out how we could heat food and water and keep ourselves warm. And so she did some searches for some like propane stove type things, right? And did a few searches for those. Well, of course, the internet has figured out that she and I live at the same IP address. Right. And so now my websites are filled with advertisements for camping gear. This family must really like camping. And so I'm getting all sorts of things. And then as a weird side effect, for whatever reason, people who like camping must also like Dua Lipa, the kind of songstress du jour at the moment. And so I get all sorts of advertising for her recent pop albums or where she has shown up on a red carpet. And I don't know what that's about. But nevertheless, I find that the context is also something that I think is misplaced sometimes when one is like trolling through, say, search results or responses to particular questionnaires or what have you, about what motivated the person to respond in a particular way. And we tend to take that as sort of this black and white thing. We provide labels for things without any sort of question sometimes about whether or not that label is appropriate or not. We build these models and find that they actually misclassify things a lot too, or inappropriately classifying things. People who are basically in survival mode, trying to keep from freezing to death, to people who like recreational camping. I'm sure that you see this all the time.
Yes,
in some
yes, I do. I mean, I basically decided that I needed to make a career move to get out of advertising. I tend to somehow say, I've gotten too cynical for advertising, so that's why I moved into finance.
That's right. Now it's also interesting that you found with your MRI data, because that's the area in which I'm do my research. So I do human neuroimaging related work. Organizations such as the National Institutes of Health here in the United States, various other European entities have undertaken major programs to try to map the human brain through a collaborative multi-site based approach. So they marshal multiple institutions from around, say, the United States to all gather data using, in principle, the same scanner and the same protocol, and hopefully the same subjects, and to gather that data and to pool all that data so that no one center is responsible for all the data collection. We're getting a national kind of representative sample, et cetera. But what we find is that the results are often dominated by site-to-site differences based upon if the scanning was done in, say, at NYU versus the University of Virginia versus UCLA, the University of Washington, whatever it is. There seems to be these enormous variations, and one may not appreciate that. And it's interesting, even though the scanner has been standardized, you're supposed to use a Siemens 3T scanner. You're supposed to use the same protocol.
It doesn't matter.
It does not seem to matter, does it?
Nope. It will find that the only answer I have found to work is you almost have to explicitly let the model control for it by telling it exactly what this thing is. So adding interaction effects to capture, kind of let the model absorb the information from the site, and then look at the residual information from there. That works better. Can you really model out all of these code confounders? I'm not sure, but it's a minimum to tell me that they existed. And often when you're trying to think about privacy preserving, they don't want you to know that because it becomes a privacy issue. And then you're losing the one tool you need to fix a lot of these problems.
Yeah, and certainly from modeling all of those interaction effects may soak up so much of your variance that you're left with nothing, and even if you did have something left, you may not have degrees of freedom, for example, to be able to associate it with anything meaningful. One of the other things that one of our listeners today has brought up is in clinical data, one of the real challenges we often have is missingness in the data, where either an entire subject will have partial record, or rather their data can't be trusted and you have to kind of code it as missing and then kind of adjust. What recommendations do you have for dealing with missingness, especially if it's random or deterministic?
I mean, I have never really found missingness to be random. So I don't like to rely on assertions of statistical assertions you get by assuming randomness. I always assume it's not missing at random. And I actually wrote a Quora answer on this whole thing. So what are your options? Imputation, I would strongly recommend against it. I think that's a bad idea. In academia, people just like to delete rows, which in industry you can't afford because there's this one instance where you have missing stuff and need to make a prediction. So now what, right? So I think it might be easier to do, but it's not the right answer. I think indicator variables are the only way forward. So basically add an indicator variable for it, and then you can impute it with whatever you want. At that point, whether you want to make interaction effects for the indicator, I found indicator variables of missingness incredibly predictive repeatedly. The quote, there is a more sophisticated way that I've seen where you basically build a model for each possible combination of available features, and then you just pick the one that's right. There was some work by Metal Zarzhansky from UT Austin looking into this. That's computationally a little bit challenging, but might indeed from a quote clean modeling or information usage perspective be the best way to go forward. So that's kind of, you can do separate models for different levels of missingness. You can do basically indicators alongside with imputation. All the other options I consider subpar.
Now, most of the audience for this lecture series are going to be in the biomedical domain. Are there any lessons that you learned while being in the business kind of world that might have any sort of translative power?
I mean, I think the large lesson of being as closely or as well-versed in the data collection process as humanly possible, and doing most of your quote data pre-processing or into features yourself. That might be a privacy concern, but I feel like I have to be part of that. And the closer the collaboration, the better. I think with the Berkeley example, that was very much at arm's length, and I think it could have been better if we had worked more closely. And so I like to build simple models that I can go and dissect for data problems like logistic regression. I know how to look at these things and have expectations and then kind of dig into it in any stuff that doesn't make sense to me. So I even if the ultimate performance is much worse than a more sophisticated XGBoost or deep learning, I like to start with something that I can at least probe for oddities in the data that I don't see otherwise.
I think that's very sensible advice, and being able to take your models apart. I really appreciated how you did that in your in several of your examples, where you're just not taking these as sensible predictors. Is only when you kind of like start to peel away the onion skin that you realize that, oh, of course, It's the people who work at the airport who need to go to the airport.
Well, I didn't see that coming, but yeah, I suppose it all makes sense.
Perfect
right?
sense, right? But a lot of maybe in some instances, a lot of people might not have appreciated that nuance, and now their model may be very highly accurate, but it's
Correct.
entirely misplaced, like selling you
Right.
camping gear when you don't really want it, right?
Yeah.
Anyway, Claudia, thank you so much for sharing your very, very wise and sensible recommendations with us, giving us some great examples and great things to think about. Thank you so much. We really appreciate that. Thank you to everybody who's out there. And with that, we'll kind of close things down. Do batten down your own personal hatches for the next winter onslaught that's coming. In that